All right, this is lecture 24 in statics. This is our second pre-recorded lecture this week in preparation for our upcoming ABET visit. So just a few quick announcements. I say here the attendance grades are up to date. I actually still have to process the attendance grades for the last lecture, but I'm pre-recording this over the weekend, so by Monday they will be posted and up to date. I also did check, and all of the homeworks are graded. We are caught up. So all of the solutions are posted, other than homework 4.3, which will be due the minute that this video goes live. And so this video is going live on Monday, October 18th. The solution will probably be posted around 5 p.m. That day. I'm going to go ahead and assign homework 5.1, the first homework on our next topic in the course, which is Centroids, and that'll be due Monday, October 25th. So that'll be due after the second exam. So long story short, after after today, once you turn in homework 4.3, you will not have any homework due until after exam 2. Okay. So what we're going to do today in this lecture is we're going to begin the next topic, which is the discussion of centroids. And I mean, there's an old joke about a statics course that it's really only about two things, and that's forces and moments. And so we've kind of already talked about that. We've already discussed forces and discussed moments, and so you could say, well, there's not really anything left for us to discuss. What we're going to be doing for the rest of the semester, and this is a perfect example of that, is we're going to be utilizing the concepts of forces and moments to solve what I would call classical problems in engineering, such as truss analyses, shared moment diagrams, etc. And the first classical problem that we're going to discuss is how to compute the location of a centroid. And this is just a fundamental and seminal skill that is required pretty much of all engineers. You're going to find centroid calculations in civil engineering, mechanical engineering, biomedical engineering, and situations involving solid mechanics, fluid mechanics, you name it. It's just a skill that's necessary. It's also, when you actually get right down to it, not very difficult. But there is a little bit of a mathematical background that goes into describing how we do it and why we do it the way that we do. And so I'm going to warn you that there's a little bit of calculus approaching. We are going to do some calculus in this lecture. This is probably one of the most calculus-heavy lectures that we have in this course period. But it's not bad. And so let's just get right into it. And I want to begin by discussing. I want to begin by discussing the motivation for studying centroids. Why are we even talking about this stuff? So I'd like to consider the following two shapes. I've got a circle here and a square here. And I'd argue that it's pretty easy to determine, where the center lies. So for instance, if I were to try and locate the center in the of these two shapes, it'd basically be right there. But I'm using the term center here because I'm not really defining what that means, and particularly what that means from a statics perspective. Okay, so I think it's pretty easy to determine, however, where the center of these shapes lie. But what about this shape? Where is the center? In fact, how would you even define the center? What would that even mean? So I guess there's two questions. Is it here? Is it here? Is it here? Is it even on the shape? There are instances where the center is not on the shape. A common example might be if you had like a donut. Like let's say you had a donut and you were trying to determine the centroid of this shaded region. Well, the centroid might be right there. And I'm throwing this term out, centroid, already because it's just sort of automatic. But the overall point is, like when I say, pretty easy to determine where the center lies or what's the center, we're not really going to be using the term center. We're instead going to be using the term called centroid. And we're going to define rigorously what that means later. But first off, I think it might be inherent that if we want to classify a shape, just a shape in general, that locating its centroid might be valuable. But where does this affect engineering? Like, why do we care in engineering? This seems like a math or geometry problem. Why would engineers care about it? Well, there are long story short, engineers don't always deal with what I would call easy shapes, and there's a lot of instances in the real world where we don't have structures or elements or components that are, rectangles or circles. They're weird, sometimes. Like we have this. This is a cross section right here of a dam. Okay, and let's say that I'm looking at this dam and I'm looking at this shaded region. There are instances where finding the location of the centroid, of the center, if you will, of that shape is very important in order to determine whether or not the dam meets the conditions of equilibrium. What about this cross section here of an airplane wing? That's certainly not a simple shape. It's got curved components. It looks sort of like this squished triangle. Like, where is the center of that? And understanding where the center or the centroid of that shape is important to determine, again, the distribution of forces. Is it able to resist lift forces? Is it able to, does it have enough surface area to generate those lift forces required to lift the plane? I mean, there's a lot of stuff there that we need to assess, and it all gets tethered to the centroid one way or another. Understanding how to locate the centroid is very critical to determining how forces and moments are distributed to a rigid body. But again, I keep going on about centroids. What the heck is a centroid? So let me try and define it rigorously. Okay. So what I'm going to do is I'm going to consider just a plate, and it has what I'll call an odd geometry. You can think of this plate kind of like this shape right here. Okay. So we're going to look at this plate. And what we're going to do is cut the plate up into a bunch of tiny little elements. So imagine that here's the plate, and what I'm doing is I'm cutting it up into like a grid, if you will, like a grid like this. Okay, and let's just consider one of those elements. We'll call it element 1. It doesn't really matter what the element is. Okay, now I propose that if let's say this is the x-axis and this is the y-axis, that there is some distance from, let's say, the center of this element. Maybe I'll use a different color here. There's a distance from the center of this element to each of the axes. Maybe we'll call this distance, I don't know, y1, call this distance here x1, since it's along the x and y axes. And we'll say the weight of that element, we'll call it delta W1. So the weight of that little differential element. We're just calling it element 1. So if we look at that element 1, that's where it's located at point x1, y1, and it has a weight of delta W. So what we can do is say, all right, I've got a force, I have a location of that force, so maybe we ought to look at this from a forces and moments standpoint. So we can apply equations of statics and look at this from a force and moment standpoint. So that's looking at one element. If I look at all of the elements in the plate, so element number 1, let's look at the sum of forces. So here's the coordinate system. Okay, if I just have the plate sitting here on the table, this. Let's say I'm looking at this plate on the table. The x-axis is to the left and right. The y is up and down. Z is in and out of the screen. So imagine Z is sort of like this axis right here. So the plate is only generating force along the Z direction. So the sum of the forces in the Z direction, what are the sum of the forces in the Z direction? It's just the sum of the weights, like each individual plate element. So delta W1, delta W2, delta W3, etc. Now, if we're trying to sum moments about, let's say, the x-axis, let's take a look up here. Let's take a look at this image, okay? How far is it from the x-axis to that plate element, right? X-axis, we'll say the moment about the x-axis for element 1 is the weight of that element times y1, because that's how far it is from the x-axis. Likewise, x1 is how far it is from the y-axis. So if you notice, and you'll see this here in a little bit, you'll notice that the subscripts are kind of flipped. So like if you want to determine the moments about the x-axis, it's the. If you want to determine the sum of the moments about the y-axis, it's the sum of the weights times their x distances. So that's not a mistake. That's on purpose. But again, I think that's pretty easy to follow. That just how far you are from, let's say, the x-axis is your y distance, etc. Okay. So what we can do is we can look at the entire plate as a whole, and we can say, all right, I took the plate and I split the plate up. So here's the plate, and I took the plate and I split it up into, you know, a bunch of different elements, and I looked at each element one at a time. And if I can determine the weight of each element, then the weight of the whole plate is just the sum of those elements. Okay. Now, what if I wanted to idealize the weight of the entire plate as just a single vector? Okay, so this goes back to some of the stuff that we've done before, where we have a collection of forces on a rigid body, and I say I want to take all those forces and idealize it as a single force. Okay, so what we would need to do is we'd say, okay, here's the plate. I need to place that vector at a magic point such that it generates the same amount of moment as all of the components themselves. So the idea is that that single vector generates the same amount of moment as the total plate. In other words, we're trying to find an equivalent system. So this is something we've actually already done before. We had a series of forces, and we wanted to collapse them into a single vector that generated the same forces and moments as the entire system as a whole. So that's what we're trying to do, is trying to determine an equivalent system. So the way that we're trying to attack this is we're trying to figure out what these distances are right here, this x bar and this y bar, the coordinates that we would place the vector that would have the same static equilibrium. And the coordinates of that point, that x bar comma y bar, is the location of the centroid. That's what we're talking about. Now, I'm using the term center of gravity, and you might go, wait a minute, what's the difference between a center of gravity and a centroid? And we will define that pretty rigorously here in a bit. But the long story short is that basically what we're trying to compute is a sort of weighted average. So for instance, if we take a look at the moments about the x-axis, it's just the sum of the weights times that y component. Well, if I want to idealize that as a single vector times this magic coordinate, so the idea, if I take this equation right here and rewrite it a little easier, I'm basically saying the sum of y times w equals the entire weight of the plate times this magic distance y bar. So if I want to solve for y bar is just the sum of yw over the sum of w. It's actually pretty easy, just the sum of y times w divided by the sum of w, or the sum of x times w divided by the sum of w. Pretty easy, okay? And that formula and that concept is really what we're going to be using for the most part throughout this topic in the class. Now, the issue is that we need to refine this estimate a bit. The problem with that formulation, with that formula, is that it depends on the size of the element that we choose. In other words, if I have this plate and I choose, let's say, these elements, I'm going to get a different answer than if I take this plate here and I look at these elements. Okay, barring my horrible artwork here, the idea is that I'm having a better estimate with this plate over here on the right, because more elements means a more refined assessment of the total weight of the plate. And so to improve the estimate, we need to reduce the size of the elements. Well, if we wanted to make this not be an estimate and actually be sort of exact and be the actual answer, we know that this is going to lead to the use of integration, right? If you remember, if you have, let's see, this should be something that you remember from calculus, right? So here's the coordinate system, here's some function f of x, and if we want to determine the area between, A and B, what we would do in calculus land is we would say, okay, let's take this and let's split it up into these rectangles, right? And then sum up the area of these rectangles, etc. And then what we learn in calculus is that definite integration is basically just a Riemann sum. We sum up those areas of those rectangles as the width of those rectangles, this delta x approaches 0, right? So we take the limit of that sum as the width approaches 0, and that's basically how we defined a definite integral. So what we're going to do is, instead of looking at this from a summation perspective, what we're going to do is look at it from a calculus perspective. So instead of saying that x bar is the sum of x times delta w divided by the weight, we're going to say that x bar is the integral of x dw divided by dw. And this notation, this x dw and dw, we're going to clarify that a little bit with some examples that we're going to do here in a bit. But the idea is that this, as the size of the elements approaches 0 and the number of elements approaches infinity, if you remember in calculus, this is just a Riemann sum. And so this is basically how we can refine the estimate in order to get what I would call the exact answer. Now, the issue is, okay, I've been talking about centers of gravity. What's the difference between a center of gravity and a centroid? Okay, well, I got what looks like a crazy amount of math here, but I want to take this math here on the slide and maybe simplify it a bit. Okay, if I have some object, some object, and I want to determine the weight of that object, I propose a very simple formula is the volume of that object times the unit weight. Okay, and the unit weight is sort of like the density. The density is mass per unit volume. Unit weight is weight per unit volume. And so this is a common term that we use in engineering. We tend to represent, so volume might be with the letter V. We tend to represent the unit weight with the term gamma. Actually, that's not typically how I would write it. I would typically sort of write it, I don't know, like that. That's kind of how I write my gammas. But gamma is a material property that's going to change from material to material. So just to give you some examples. So if you wanted the unit weight of, let's say, water, in engineering, we typically take that as 62.4 pounds per cubic foot, right? Let's say, here's a common one for steel. Value for steel is 490 pounds per cubic foot. These are just a couple of examples. But the idea is, if I know how much the object weighs per unit volume. If I multiply it times the volume, I'm going to get the weight. Okay, so where does that come into here? Well, if I'm talking about some plate, right, with some thickness, right, let's take a look at that element that I cut out. That artwork I know is horrible. Let me see if I can clean that up. So let's take a look at that element. So this is that delta W term. So I propose that the weight of that element is going to be the unit weight times the volume. And I propose that the volume of this plate is simply the thickness times whatever that area is. So if you see here how I've taken this center of gravity term and I've sort of made it a little more complicated. Instead of x times the weight, I'm saying it's x times this gamma t area. Okay, so that's where I'm getting this term here. So where is this valuable? Okay, so the center of gravity works pretty well for objects that have, well, I would say a variable thickness or a variable unit weight. But a lot of times in engineering practice, we often deal with components and elements that are of uniform weight and uniform thickness. So all those gamma terms would cancel. All the thickness terms would cancel. And instead of dealing with a weighted average of the object's weight, we're dealing with a weighted average of the object's area. And so if a center of gravity is defined as the point in which where the weighted average of the weights would be located, this is where the weighted average of the areas are. And so this is the definition of the centroid. Sort of shorthand that we use for the centroid is just the sum of XA over the sum of A, or the y bar is the sum of YA over the sum of A. And this is actually going to be the most useful term of the formula that we use later on in the course. When we come back, this is going to be very, very, very useful. Okay. So let me sort of explain where how the centroid is used in engineering practice. So, for example, a couple of things that's worth mentioning. So, a lot of times, we don't deal with simple shapes. We deal with weird shapes. What we tend to do as engineers is we say, okay, let's take this concept here, let's take this shape right here, and let's split it up into a bunch of, I would say, basic shapes like rectangles, triangles, semicircles, etc. And let's determine the location of each of those. And if we, or sorry, the centroidal location of each of those. And if we can determine that, then we can basically use our weighted average component formula to determine the centroid of the whole thing. And that's what we're going to do in the next lecture. What we're going to do in this lecture is we're going to focus on trying to determine the location of the centroid for each of these individual shapes. Now, I'll go ahead and tell you what we end up doing in engineering practice is we end up using basically, if you go into the back of your appendix in your statics textbook, there's going to be a table that says tables of locations of centroids. It's probably in the cover of your book as well, depending on if you have a physical book or an ebook. But a lot of times these textbooks, your FE reference manual, steel manual, what have you, centroid locations are pretty easy to find. The idea is that your composite shape is going to be comprised of a bunch of simple shapes, and so you can use these centroid references to make the calculation a lot easier. What I want is for you to understand how those centroid references work, okay? And that's going to sort of be the focus of the example today. So what we're going to do is we're going to take a mathematical function and see if we can use these terms here to determine the location of the centroid. Now, because we're looking at this from a geometry perspective and instead of a weight perspective, instead of looking at this from the terms of weights, we're going to look at it in terms of areas. I know my camera here is covering a little bit on that Y bar, but yeah, I think you kind of get the idea. The other thing I think that's worth mentioning before we jump right into our example, and I think you'll kind of see what we mean when we start getting into this, is that even if you're dealing with a body that is comprised of different materials, of different weights, so let's say you're trying to determine the center of gravity of a car, typically what an engineer will do is they would say, okay, that's a really complicated problem, but the car is comprised of discrete components of uniform materials. So maybe what we'll do is we'll determine the centroid of this particular engine component and this particular tire and this particular cable and this particular hose, et cetera, et cetera. And then all it is just a weighted average of all of those components, but you're still using the centroid to perform the calculation. So it's just a fundamental calculation that you're going to see all over in engineering that's very valuable. Let's get into an example, because I think that the easiest way to explain how the centroid works and how this comes about is to perform an example. Okay, so we're going to determine the location of the centroid of this region. Okay, now if you notice, let me pull up my notebook here. I know I'm going to have my ink annotation things pop up, and we can make that go away. All right, let's go to this. Okay, so this is the shape that we're going to determine the centroid of, and so it's this region bounded from x equals 0 to x equals 3 of the curve y equals x squared. So it's this like parabola region, and I want to determine where the centroid is, like where is the x comma y. So if you wanted to think about this from a physics perspective, if I were to print this, let's say I take this bounded region and I took it to a 3D printer and I printed it out. The idea is like that's the point where I could set the plate and it would balance is kind of the idea. Okay, so what we're going to try and do is determine where that point is. Now, what we're going to do is, for this problem, this is something I kind of wanted to mention here in this, this box here. I want this problem to be a little more numbers heavy. I'm trying to soften the algebraic blow, if you will. So this is y equals x squared, and I'm basing it on a particular region bounded from x equals 0 to x equals 3. What we could do is we could say, well, what about instead of x equals 3, what if it's x equals a? Okay, and instead try and derive a formula that's a little bit more robust. But I'm not going to do that for this example because I just want you to kind of have an idea of what we're doing here. So let's take it slow, and I think you'll see where we're going with this. Okay. So the first thing that we're going to do is we're going to see about computing the area. Okay. Now, one of the things I want to introduce to you, and I've kind of been doing this a little bit in the slideshow, but I kind of want to do it formally, is, you know, if you've had calculus, you're probably used to this notation, AB f of x dx. Okay. What I'm going to be doing is I'm going to be using sort of a shorthand notation, and I'm going to say that this is the integral of dA over the area. That's just sort of my shorthand way of doing it. And I'm doing that because I want to sort of think of these problems in sort of these dA terms, because it makes it a little easier when you're looking at things with respect to both the x-axis and the y-axis. It makes that that mathematics a lot easier to figure out, and you'll understand what I mean when we start getting into some of our moment computations. Okay, so let's redraw our curve here. So this is our curve. And we're determining, you know, the centroid of this area. Okay, in order to determine the area, what I want to do is I want to see if I can define what's going on with this rectangle. And I'm sure some of you are probably thinking, look, if you want to find the area, just integrate x squared from 0 to 3. Like, why are you harping on about this? This is pretty easy. I understand that, but this is going to be kind of important to think about this later when we start looking at the other axis. So just bear with me on this. Okay, so let's see if we can come up with some observations here. So this point here is x equals 0. This point here is x equals 3. Okay. Now, I propose that the width of this rectangle here is, I'm going to call it dx, okay? Because remember, when we're thinking in calculus, Sam, we're thinking about these slivers that have this infinitesimal little tiny width. And remember, dx is that, you know, super, super, super tiny width, okay? And as for the height of this triangle, I'm going to say that the height of this triangle is y, okay? Whatever y is, all right? And remember, this function here is y equals x squared. So I want to think about this in terms of dA, and dA is basically the area of this little rectangle. So area of differential rectangle. And in this case, dA is going to be y dx. But we know what y is. Y equals x squared. So this is x squared dx. So if I want to find the area, I just integrate these dA terms over the area, which is the integral from x equals 0 to x equals 3 of x squared dx. Okay, and this might seem like a little bit of a weird way of writing it. Like, why are you writing the x equals 0 and the x equals 3? Like, why are you doing it that way? There is a reason for that, okay? And trust me, it'll become clear later on. Okay, so at this point, this should be a pretty simple calculus problem. The integral of x squared dx is x cubed over 3. integrated from x equals 0. Actually, let me write that out. X equals 0 to x equals 9. And so that's 9 cubed over 3 minus 0 cubed over 3. And so area equals 9. Okay. Sorry. Oh, nope. Had a mistake there. That's supposed to be 3. It's not 3 cubed. I was looking ahead. Sorry. 3 cubed over 3. All right. So that's the area. The area equals 9. And I want you to keep that in the back of your head. Okay, so that's area. Now, what I want to do now is I now want to determine the first moment about the y-axis. Okay? Now, what do I mean by first moment about the y-axis? This is a little bit of a new term. So here's what I mean. Before we did that, we integrated dA. Now what I want to do is I want to integrate dA times the distance from the y-axis. And so the question is, how far is this rectangle from the y-axis? What is this distance right here? That's the moment arm. What is that distance? That distance is x. Okay, so now what we're going to do is integrate x dA. Okay, so let me rewrite that a little bit more clearly. X dA. Okay, so now what we're going to do is integrate. We're going to do the same integral, only instead of integrating x squared dx, we're going to integrate x equals 0 to x equals 3 of x times x squared dx. So the first moment of area is when I multiply the dA term times x. So for example, if I were to change this to, let's say, x squared, it would be the second moment of area. Or if it was x to the fifth, it'd be the fifth moment of area. And so the reason I'm using this term is because later on we are going to see second moments of area. We're going to look at that a little bit later. We're not going to have to worry about that right now, though. Okay, so what we're going to do is integrate this out. So we have the integral of x cubed dx, which is x to the fourth over 4 from x equals 0 to x equals 3. It's not x equals 9. So 3 to the fourth over 4 minus 0 to the fourth over 4 is 81 fourths. Okay? So therefore, x bar is the integral of x dA over the integral of dA. Pretty simple. So 81 fourths divided by 9, that's pretty easy. We get 2.25. So that's actually one of your answers right there. That is the location of one of your centroids. That is one of the coordinates of the location of the centroid. So to put it in perspective, okay, if I scroll up here, I'm trying to determine the location of this point right here. I propose that the x-coordinate is 2.25. We don't know what the y-coordinate is. We haven't figured that out yet. Okay. Now, one final note before we jump ahead is I do want to say note, if we did the integral of x squared dA, this is what's called the second moment of area. So second moment about the y-axis. And we have a name for that. We call it IY. We're going to see this later, but IY stands for what's called the moment of inertia. And the moment of inertia is a really, really valuable piece of data in mechanics of deformable bodies. It tells you how stiff an element is when you're bending it. And we'll talk a little bit about later about how that corresponds. But it's actually a pretty useful data point. Okay. Now what I want to do is I want to go back to the graph. Okay. And I want to do something a little different. And there is a reason for this. So this is X, this is Y, and here's our graph. And here's the region. Okay. And we're going from x equals 0 to x equals 3. So I want to look at this a little differently. This dimension here is 3. Okay. And this dimension here, hold on. Let me erase this a little bit. I want to make this neat. Okay. Now, let's also be clear again what this line represents. This line represents y equals x squared. Okay. Now, what I'm going to do is I'm going to look at this a little differently. Okay. Instead of integrating from left to right, integrating horizontally, I want to flip it. And I want to integrate this way. And so what I mean by that is I want to now look at this rectangle. And the reason why I want to look at this rectangle is because what we need to figure out is this. We got to figure out that, and we have to do that so that we can determine y bar. And so the most systematic way of doing that is to look at it this way. Okay, so let's see if we can redefine this rectangle a little bit. Now you got to be careful about this. Okay, first off, let's look at the thickness. Okay, I propose that the thickness is now dy. Okay, now what about the width? Okay, well, let's pay attention to some things. Okay, what is this dimension right here? What is this dimension? Okay, this dimension is the distance from the origin along the x-axis. Okay, so I propose that this dimension is x. So if this is x and that's 3, what is this right here? This is 3 and that's x. So this is 3 minus x. Okay? Does that make sense? Hopefully. Because, think, if this was 15 and this is x, then, let's say this is 15 and x is 8, the rest is 7 because it's 15 minus 8. So if x is 1, then that little rectangle that I've drawn here on the screen, it has a width of 2. Okay? So, therefore, we got to we got to go back to square one. We have to go back to dA. I propose that dA is 3 minus x times dy. Now that's a start, but we're not quite there. And the reason we're not there is because we have 2 letters here. We have 2 variables, x and y. We need to make a substitution, okay? Because I now want to write everything in terms of y. How do I do that? Well, let's go back to the equation. If y equals x squared, x is the square root of y. So I'm going to rewrite this now as 3 minus the square root of x. Sorry, 3 minus the square root of y dy. Now, if you're a little confused as to if this is the right way of doing it, there is a perfect test for that, and that is to compute the area. Now, here's the thing. We already computed the area, so we know what the answer is, but I want to do it using this new notation, using the rectangles this way. So now we're integrating in terms of y. So what we're going to do is we're going to integrate from y equals 0 to y equals 9, okay? Because we're going from top to bottom. And what we're doing is summing up those rectangles. And those rectangles are 3 minus the square root of y dy. So, the answer should be 9. Let's see if it is. So, this is 3 minus y to the 1/2 power. So, I think that makes the integration a little easier. So if I'm integrating 3, the integral of 3 is 3y minus, and if I'm integrating y to the 1/2, I take y, I add 1 to the power, and then 3/2 becomes the denominator, and I'm evaluating from y equals 0 to y equals 9. So 3 times 9 minus 9 to the 3/2 over 3/2 minus 3 times 0 minus 0 to the 3/2 over 3/2, right? Plug in the top number minus plug in the bottom number, okay? What do I get? I get over here 27 minus, okay, now hold on, let's pay attention here. So we have 9 to the 3/2, so we take the square root of 9, which is 3, right, to the third, which is 27, over 3/2 minus, and all this is 0. And so 27 minus, and this is 2/3 of 27, right? Flip and multiply. So this is 27 minus 2/3 of 27 is 18. Area is 9. So we got the same area before. So that didn't change, right? But what's valuable is that writing it this way, I can now do this. I can now say, now I got to do that. See, before, writing the dAs in terms of x's would have made this potentially very, very challenging. So this is making it a lot more systematic. So y equals 0, y equals 9, y times 3 minus the square root of y dy. Oh, I can do better on that. Now we've got something we can chug out. So first off, before I chug all this out, this is a classic integral problem. You can plug this into your Casio. It'll do this type of stuff for you. But if you want to chug this out, and maybe I'll pull up the Casio here in a little bit to show you how this is done. Pretty straightforward. So integral y equals 0 to y equals 9 of, so y times 3 is 3y. And then we have y to the 1/2 times y, so this is y to the 3/2 dy, which equals, the integral of 3y is going to be 3/2 y squared minus, and then we're going to have y to the 3/2, so it's going to be y to the 5/2 divided by 5/2, or 2/5 y. Then y equals 0. Y equals 9 equals, and so we plug in the top number minus plug in the bottom number. I think if we plug in the bottom number, we're going to get 0. So all it is just 3/2 times 9 squared minus 2/5 times 9 to the 5/2. Oh, 5/2. Sorry, 9 to the 5/2. And so when you chug this out, you end up getting 243 over 10, or 24.3. And just to make sure that we're comfortable with this, let me break out the Casio, just to make sure that we're good. So Casio. Let's see. There's that. There's that. So on the Casio, let me move my calculator pad here so it's not getting cut off by my camera. There's a button here under alpha that will do integration. And so now the integral is already in terms of x, so I'm just going to use the x term instead of the y. And so all I'm going to do is plug in this integral here, just using x's. So alpha x, here I'll just use my pen here, times 3 minus root x, and then 0, 9, and 24.3. You get a little bit of a decimal carrier here because the Casio is doing this numerically. So it's using numerical methods, so it might trail off a little bit, but exactly the answer is 24.3. If you have a more advanced calculator, it'll probably give you the answer exactly. So therefore, y bar is, the integral of y dA over the integral of dA, which is 243 over 10 divided by 9, which is 27 over 10, or 2.7. So y bar is 2.7. Or if you scroll up here, we can say 2.7. So that's the answer. That's where the Centroid is. So if I were to, again, take out a 3D printer, print that thing out, stick it on the head of a pen, right there at that point, it will stay balanced, because that is the point where the moment contribution by that plate is 0. So holding it there, the plate will not want to rotate, so it will stay balanced. Hence, what we're talking about here. So hopefully, you found this is pretty straightforward. I mean, this might be a little bit new, how we're taking the rectangles, and instead of writing them up and down, we're writing them sort of side to side. But the reason for doing that is to make this particular integral a little bit more straightforward and systematic to perform. What I'm going to do for your homework assignment, I'm actually going to pull up the homework and pull it here on the video, is I want to see if you can perform the integration for this. So what we have here is, let me make this go away. What we have here is a triangle, and I want to see if you can derive the coordinates of the location of the centroid of that triangle. Okay, now it's symbolic, so there's B and H instead of, like what we did in this example where it was 3 and 9. I'm actually leaving it in terms of B and H. There is a reason for that, okay? And I'll show you why when we come to class, or when we discuss this after the second exam. But the long story short is that if you open up your appendix or open up the cover of your textbook, what you're going to see is formulas for the centroid of a circle, the centroid of a semicircle, the centroid of a rectangle, the centroid of a triangle. And it's going to tell you what the coordinates of the location of the centroid of those shapes are with respect to terms like B and H. And so later on, we're just going to use them. We're just going to look it up, and we're going to say, oh, it's 4r over 3 pi. Just use that. But I want you to have an understanding of where those values come from. So I want you to derive a centroid on your own. And this is arguably one of the easiest ones to do on your own. Okay. What you're going to need to do is determine the location of x bar and y bar. And so I've given you a couple hints. And so this region is this triangular region bounded from x equals 0 to x equals b of this line. And so the first hint that I'm giving you is what is the equation of that line? What is the slope of that line? What is the intercept of that line? And if you can determine y equals a pile of junk as a function of x, it makes the integration a lot easier. When you're doing the integration, make sure that you treat b and h as constants, just like what we calculation that we just did, where we treated, like 3 as a constant or 9 as a constant. If you treat b and h as constants, just as you treated 3 and 9 as constants in here, and you know the equation of the line, it's going to make it pretty straightforward. Probably the hardest part is this part right here, where you have to determine the width of that horizontal component. I think the best thing to do is actually draw a sketch out. Here's the line, here's the rectangle, determine the dimensions of that rectangle, actually draw it out. If you don't draw the sketch, I think it actually might make the assignment a little harder. Take the time and draw it out, and I think you'll find this is pretty straightforward. When we come back after the second exam, we're actually going to use these, so no more calculus, we're going to use these to do some more real-world problems. Okay, that's all I have for this lecture. I will see you all when we return on Wednesday for our Exam 2 review, and then we will pick up our Centroids discussion after the second exam the following Monday. That's all I have. I will see you then.